Hello. Today we're going to investigate the inverse square law for gamma radiation using a 𝗟𝗀 source. Here I've got my Geiger-Müller tube connected to my counter, acting as a Geiger counter, and I've got my stopwatch down here. So the first thing I'm going to do before I do anything else is measure background radiation. I'm going to measure it over 5 minutes, and you're not going to watch the full 5 minutes. All I'm going to do is press reset and start on the stopwatch at the same time, and when 5 minutes has passed, I'll make a note of this number. While we're measuring background radiation, we can read up on our standard operating procedures. These are, of course, different from school to school, but generally speaking, they're going to be the same because they're all taken from L93 in our school anyway, and it would be daft of us not to follow the guidance from L93. So there's basic stuff there about not handling the source directly with your hands, using tongs and all the rest of it. And here we've got our specific risk assessment for what we're using, where it tells us that we should keep the source at least 10 centimeters away from our body using forceps. Okay, we're nearly finished measuring background. 57, 58, 59, stop. 78 counts in 5 minutes. That's what that says. So we can get this written down here, 78. And then we can calculate background radiation in counts per second, or becquerels. Just went and got this horrible calculator. So 78 counts divided by 5 minutes and 60 seconds per minute. About 0.26 becquerels. That's what background radiation is. So let's write that down. So background radiation in the units of becquerels, 0.26. And that'll be important for later. Okay, now we can retrieve the source. So here's our radioactive source we're going to be using, which is 𝗟𝗀_60, and this claims to be a gamma source. We'll have to check that out because I'm not convinced that 𝗟𝗀_60 only emits gamma radiation. Inside we have this lead cover, and I'm only using the forceps there to help me lift the cover off, otherwise you have to get your fingernails underneath it. And here is our gamma source. Not allowed to look directly into it, but this is a camera, so I can definitely shine it directly at the camera. If you ever wanted to look inside one of these sealed saucers, one of these cup saucers, here's your chance. I'm not going to look, but I am going to point it at the camera, and hopefully I'll line it up well enough so that you can clearly see. It's not that exciting, it's just a silvery colored metal underneath the mesh. That is emitting gamma radiation. So we're going to use that source and the equipment, and we're going to place the source at different distances from the Geiger-Müller tube entrance and measure the activity. Now there's a few problems with this experiment. One of the problems is that the Geiger-Müller tube I'm using here is not the best Geiger-Müller tube for detection of gamma radiation. Probably only going to be detect 1 or 2% of the gamma radiation. If I wanted to detect more of the gamma radiation, I could use this detector. I'm just going to lift it out. This obscene looking detector. This is better for detecting gamma radiation. However, I'm not going to use this because I'm actually not sure where in this the detection will take place. And if I'm measuring activity that's detected divided by, well, not divided by, I'm measuring it with respect to distance, I need to know exactly where I'm detecting it. So although the detection efficiency of this Geiger-Müller tube won't be great, at least I will have some measure of the activity. It's not activity, it's the count rate that is measured. I'll have some measure of the count rate from a particular position, from 0 centimeters on this distance scale. The second problem is this distance scale, the resolution is pretty terrible. It's to the nearest centimeter. But actually that'll be okay. I'll just incorporate uncertainties, and actually that might work out to my benefit in the end, because the results might not actually be very good. We'll wait and see, won't we? High uncertainties are a good way of making your results better. Right. Now, what I can do a bit later is research and see whether this cobalt-60 source is just emitting gamma. And if it's not, that might help explain some of the funny results we might get. I mean, I'm saying might because I've done this experiment quite a few times. I've just reset the Geiger-Müller. Sorry, not the Geiger-Müller tube. I keep tripping over my words today. I've just reset the counter, so it's on 0. Now we're going to lift out the source, and we want to handle this as little as possible. And I have this sort of Panax-style plastic holder. So I'm going to lift the source out. I'm going to grip it. Oh, you can't see what I'm doing. Let's move this to here so you can see. So I'm going to lift the source out. Then I'm going to grip it from underneath so it doesn't move. Push the holder over it. And then making sure that I'm not pointing the holder towards myself, the common mistake students make, I'm going to point it over there and position it 3 centimeters. And I'm going to then measure for, I could do 2 minutes. Looking at the clock, I don't know if I've got time, but yeah, I'll do 2 minutes. So I'm going to position it in each of these positions for 2 minutes to get some data and record that, obviously, in my lab book. Where's my lab book? There it is. Right. So we're going to start the timer and press start at the same time. There we go. That's now counting. Now, as I say, that source is emitting a lot more radiation than that Geiger counter can show because the detection efficiency isn't great. Now, while it's going, I've got 2 minutes to draw my table. So let's draw my table. First column here is going to be distance, which I'm going to use centimeters. And the second column here is going to be the counts per 60 seconds. And I'm leaving space for additional columns because I'm definitely going to need them. Around here, keeping my distance away from the source, making sure that I'm not exposing myself as much as possible, or as little as possible I'm exposing myself. How many measurements will I take? 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't really want to do more than 10 because then my graph's going to get a bit silly. So I'll just do 10. 9, 10. We could go for a larger range. Absolutely, we could. But I really don't want to. The more data, the better, of course, but I really don't want to. I'm not going to draw the other lines on my table yet because I don't know how much more data I'm going to, how many columns I'm going to need yet, so I'll leave that. The distance at the moment is 3 centimeters, so I'll just write that as 3, not 3.0, because this only measures to the nearest centimeter. And I don't know if the stopwatch screen is visible, but we're coming up on 2 minutes now. So, getting ready to hit stop. And I'm not going to show you every single one of these because that would become tedious. 4402. That's what I write down here. 4402. Now, I have actually just noticed a mistake. I measured for 2 minutes, but I wrote down counts in 60 seconds. So I need to correct my column header. 120 seconds. There we go. Silly, silly mistake. Mistakes happen. None of this is prepared in advance. Okay, then I carefully move this to a new position. Let's go for 5. Handling it as little as possible. Write down 5 on my table. That's the next distance. Press reset. Actually, I press start and then I can press reset and start on the stopwatch at the same time. And then we wait 2 more minutes. And I'm not just going to let you sit there and watch this happen. I'm going to skip ahead with the magic of video editing. I should point out as well, just before I do that, you'll notice that the Geiger counter isn't clicking. And that's because I haven't connected the speaker or amplifier, mainly because I wanted this set up to look as low clutter as possible. There really isn't much advantage to hearing the clicking unless you like that sort of 1980s Chernobyl aesthetic. So let's skip forward until I've got all my data. Okay, so I've got all my data. It's now time to put the source back in the holder and put it back in the safe. We don't need this anymore. So the less time we can be exposed to it, the better. There we go. Before I put it in the safe, I will have to inspect it for damage. I don't expect to see any, but it's part of the standard operating procedures. And then I can put all this equipment away and do the analysis. But I have actually started with the analysis already. Rather than just sitting there, there we go. Rather than just sitting there, I started doing the calculations. So each of these is the number of counts in 120 seconds. We finished on 76. The count rate, which is each of these divided by 120. So the last one is 76 divided by 120, and that gives me 0.63. And then each of these I'm subtracting, so 1.30, subtract background radiation in becquerels. That gives me, it actually went up a bit there, didn't it? 1.04, although it's not huge activity. So 1.03, subtract 0.26, 0.77. You could probably do these in your head if you're good at mental arithmetic. I am not. So you can see 30 centimeters away, the corrected count rate is really, really low. It's comparable to background already. So you're not getting that much of a dose from this thing. And the analysis I've chosen to do is a log-log analysis, because if the inverse square law is applicable in this situation, then I would expect the gradient to be -2. And I'll go through the analysis here for that in a second. Let's get the source put back in the safe first. Okay, the equipment's away, my hands are washed, so it's time for the analysis. I've already done the log to the base 10 of all of these. Note the unit. I'm now doing log to the base 10 of all of those. So I just lift out my horrible calculator. Log 36.42 equals 1.5. Now, I think technically, is 36 coming out as 1? Oh, well, that's what it is. So this would be 1.5613. I'm not going to be able to plot that, though. It should technically be that, so I'll record that. And the reason for that is that the first digit is to do with the order of magnitude. There we go. So the first one is to do with the order of magnitude, and the rest of them are basically the significant figures. So if this is 3 significant figures, I have to record that to 3 significant figures after the decimal point, because it's log base 10, so that everything before the decimal is just the order of magnitude. That's how logarithms work. So log base 10 of 8.09 should come out as 0 point something. 9079 is the order of 4 significant figures. And that should actually be 3 significant figures, because that's a 3 significant figure one. So I should have rounded that one. Never mind, I'll do the next one. So log 3.59, this should be 0.555, 3 significant figures. 0 before the decimal point is the order of magnitude. Fine. I'll fill the rest of these in. You see, I've messed up with this one. This should be 3 significant figures, so that should be minus 0.0177. Hopefully you can see that okay. Right, log of 1.04, 0.0170, and then log of 0.77, negative 0.114. No, it should be 2 significant figures. So why have I given that to 3? You see, I'm messing it up left, right, and center. That should be 2 significant figures now. And then the last one is the log of 0.37. There should be negative 0.43. Can I just check that one? Log of 0.77. Yeah, that is what it comes out as. Okay, next up, we are going to plot our graph of, well, let's think about the analysis first. Again, I'm just doing this live, so some of this is, let's just rotate this around so it's easier for me to write. We think this is going to be an inverse square law, which is an example of the power law. So we think that the corrected count rate as a function of the distance is going to be equal to some constant multiplied by the distance to some power. And we don't know what that power is. That's what we think. So if that's the case, then the log of that constant is going to be equal to the log of k plus n times the log of d. And in my video series, this is all about transition work from GCSE to A-level. I go through how to analyze and get to that stage. It's just using the laws of logs. Right, now if we plot this on the y-axis, and we plot this on the x-axis, then this is the gradient, and this is the y-intercept. And what we're interested in is, so that's plus, that's times, that's equals. What we're interested in is that the gradient is -2. If the gradient is -2, great success. So we expect gradient to be -2. Expect gradient of log C versus log D graph to be -2. And we can look that up if we want to reference our expectation. It's an inverse square law, so we could actually just look it up in the textbook. It's not very interesting to reference. Okay, let's zoom out a little bit with the camera so that we can... Well, you can see all the clamp stand then, can't you? I'll figure this out, the zooming, so that you can see the graph as I draw it. Right, that's about as good as you're going to get. So, sit myself back down again. Let's choose our scales. On the x-axis is going to be log D, which is this one. So going from less than half, let's say 0.4 to 1.5, 0.4 to 1.5. So 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1, 1.1, 1.2, 1.3 doesn't fit. So we're going to have to go something like 4, 6, so 0.4, 0.6, 0.8, 1, 1.2, 1.4, 1.6. The data will occupy about half the page, but that's going to be the most sensible scale. So we don't have to push it right to the edge, is the point. Right, now let's do this one. We're going to go from about -0.5 up to 1.6. So -0.5, 4, 3, 2, 1, 0, 1, 2, 3, 4, 5, 6, 7, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, sorry, 0.5, 0.4, 0.3, 0.2, 0.1, 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. That's not going to fit. So let's try in twos. We're going to go not from 0.5. Let's go -0.6, 0.4, 0.2, 0, 2, 4, 6, 8. So that's going to be 1.0246. Right, that would make sense. So we can go from here up. And this scale is going to go from -0.6, -0.4, -0.2, well, no, it's just 0. -0. And then it's going to be 0.2, 0.4, 0.6, 0.8, 1.0, 1.1, 1.2, 1. Messed up the scale. 1.2, 1.4, 1.6. Let's just check I haven't been a numpty. 0.6, 4, 2, 0, 2, 4, 6, 8, 1, 2, 4, 6. Yep, okay. A bit of a numpty writing my numbers here, but that's okay. And I can label this with a log of C measured in becquerels, where C is the corrected count rate. Now my x-axis going along here, and I'm going to draw it through there because that makes people more comfortable. I could draw the x-axis down here and be quite happy, but people prefer to see an x-axis along 0, so that's what I'll do. We were going to go from 0.4, I think it was 681, 1.246, wasn't it? So 0.4, 0.6, 0.8, 1.0, 1.2, 1.4, 1.6, and there's no point writing numbers beyond that because it doesn't go that high. And this is going to be the log of D in centimeters. Okay, now we plot our points. Now you may be wondering, why haven't I used the right number of decimal places here? Because it should match what's in here. But over here it keeps changing because of the nature of the calculation that was done. So there's not that much point trying to insist on that rule in this case. The number of significant figures is changing. I'm not going to keep it all the same. But also, what can I actually plot here? Well, each of these little squares is 0.02. So I suppose I could have put extra zeros on the end of here, and that would have been more correct. So let's just pop these on. Should have given myself enough room. There we go, that's more correct. And looking along the x-axis, I can plot to the nearest, well, each one of these is 0.2, so 0.02. So again, I should have put little zeros at the end of these. There we go. So just a little bit of intelligence when you're plotting. Okay, 0.477, close to 0.48, which is going to be 4 little squares across, and 1.56. So 1.56 is going to be 3 little squares above that, so it's going to be there. I'm not going to do all the points. Well, I'm not going to talk through all the points. I'm just going to plot them. And fast forward the video. So, but I'll do the next one. So this is going to be 0.70, which is exactly between there and there, and then 1.17. So 1.1, and then halfway between 1.16 and 1.18. So that should be there. Now, I'm plotting these points, but I haven't thought about uncertainties. There's enough data. Hopefully the data will be on a nice straight line. If not, then I might do a line of best fit that's a worst and best case scenario, and then we can use that for our uncertainties. But otherwise, I'm not sure we can analyze uncertainties. The trick with this one is to get so much data that the uncertainties become so small we don't care about them. But I'm just going to plot the rest of the points now and skip ahead. There we go. There's all my data plotted, and actually it looks pretty good. There's some interesting points, like this one here seems to be a bit on the low side, should have been a bit higher. That was around about here. We thought, oh, that result went a bit funny. So the random nature of this decay means that could actually just happen. It's not necessarily a mistake, but that is interesting. There's another one that seems a little bit on the low side down here. But everything else lies pretty much along a straight line. So I'm going to go with the straight line here and ignore those 2 points as my line of best fit. And then I'm going to go with another line of best fit where I do include them, which is going to be a tad steeper. And that's going to be my worst acceptable line of best fit. So worst acceptable line of best fit, including all the points, a line of best fit, not including all the points, discarding these 2. So discarded for line of best fit, like that. Now we're going to do our usual gradient calculation. I'm not going to use a purple pen because it smudges. Let's take a point up here where the line crosses some nice convenient grid lines. Hopefully it will somewhere. There's pretty close. So this is at the coordinate 0.50 and 1.52. And let's do the same thing down here. Oh yes, right at the bottom there. And that is going to be at the coordinate 1.64 and negative 0.56. I'm going to do the same thing with the worst acceptable line of best fit, that point there. So you know I'm looking as far apart as I can. You can draw your triangles and things. I'm not going to. 0.48, and on the y-axis 1.64. And I'm going to do the same thing all the way down here. Where does it cross the grid lines nicely? Come on, give me a nice place where it crosses the grid lines. Oh, it really doesn't, does it? Closest places, no. I don't want to interpolate within the grid lines. Go on, give me a nice one. Right, we don't have a nice one where it crosses the grid lines nicely, so we're just going to have to go with the nearest point. The further away it is from this point, the more accurate it will be. So I reckon we should just go with, it doesn't really matter, let's just go with this point here. And I'm going to have to do some interpolation. So that is going to be 1.54, and on the y-axis it's actually negative 0.4, and then that's 2467. So I'm having to interpolate a little bit. All right, gradient, moment of truth. So line of best fit gradient equals, I'm going to run out of space there, aren't I? Let's see if I can cram it in. So that's going to be negative 0.56 subtract 1.52, and then divide that by, down here, 1.64 subtract 0.50. And then we're going to chuck that into our horrible calculator. Here it is. Yuck. Won't even turn on. That's how much it dislikes me. So negative, there's a different button for negative than it is from subtract. Oh, everything about this is awful. Right, negative 0.56 minus 1.52, and then 1.64 minus 0.50, and that gives me, oh, look at that, negative 1.82. And we wanted 2. Now, there's no units for this because it's a logarithm divided by a logarithm. So there's no units. That is the gradient. I could calculate the intercept if I wanted to know what the k was in my calculation. But actually, I don't need the k. I'm not interested in the k, really. Right, let's do the same thing for the green one. So this is worst acceptable line of best fit gradient equals, and we're going to type these numbers in. So negative 0.47 subtract 1.64 divided by 1.54 subtract 0.48. Always check my calculations, never trust me. I do make mistakes. So negative 0.47 minus 1.64 divided by 1.54 subtract 0.48 should give me, oh, look at that. That's even better. Maybe I should have included that that point. So negative 1.99. We were after negative 2. That's really, really close. I'm very pleased with that. But even so, actually, it's not quite right, is it? So we can put down here that the measured n, that was the power, is equal to negative 1.82 plus or minus, and it's going to be the difference between these two. So that's going to be subtract the previous, I don't even know how to do that. So let's just go 1.99 subtract 1.82, and don't worry about the sign. Okay, so plus or minus 0.17. So upper bound n is equal to negative 1, or lower bound n. Lower bound n is equal to, so close to n equals negative 2, but not close enough. What a shame. So close. And now we've got to think what we were going to look up. We were going to look up and see whether 𝗟𝗁 actually is a gamma source, only a gamma source, because it might not be. And if it's not, then we're going to get more radiation than we would expect. I mean, what would actually happen is if it emits some beta, alpha we wouldn't care about, but if the 𝗟𝗁 also emits beta, then the beta attenuation is going to be an exponential attenuation, and you're also going to get the inverse square attenuation as well, because as you move the Geiger-Müller tube further away from the source, you've still got inverse square law, but you've also got absorption of beta, which you don't get with gamma, at least not by any amount we can really measure. So that would mean that it would decrease in activity faster than the inverse square law. So that's not quite what this is saying, is it? This is suggesting it actually decreases lower than that. So maybe it is just gamma and the results weren't quite good enough. I mean, it's so close, you could probably put that down to random noise, although I did an error analysis and perhaps you can't. Maybe I've discovered some new physics. Let's go do some research. Right, our friendly Wikipedia page, cobalt-60. Half-life is, well, this source is probably about 30 years old, so yeah, good luck. Let's keep going. Oh, look at this. Okay, so we get cobalt-59 becoming activated by absorbing a neutron, and then it appears to decay by beta decay. Not gamma. Decay mode, beta decay. How interesting. Oh wait, gamma spectrum of cobalt-60. So it does emit gamma radiation of a couple of different energies. So we have beta decay immediately followed by gamma, and the gamma is from an excited, it looks like it's from an excited, or maybe it's, no, it won't be metastable cobalt that's decaying by gamma. That would be way before. What's the half-life of that? The half-life of that's in minutes. So we can ignore that. We've already got the cobalt-60. So we've not got any metastable cobalt-60 here. So we're not worrying about that bit. So we've got all this cobalt-60 with a 5-year half-life, going to decay by beta, and then the daughter, the decay product, which is this nickel-60, is metastable and will decay by gamma radiation. I'm guessing we're detecting these gammas. Why are we not detecting the betas? That's an interesting problem. So why do we not detect the betas? Because this suggests we should get beta, and if we get beta, then the activity would fall off faster than the inverse square law. The measured count rate would fall off faster than the inverse square law, and in that case, we would have a power that's greater than -2, but less than. You know what I mean? A larger magnitude than -2. So not emit beta. Presumably, the beta gets absorbed somewhere. Oh, look at that! Physics stack exchange. Physics stack exchange. So cobalt-60 is a gamma source, only emits gamma, do not give higher count than only gamma sensitive tubes. Technically it's a gamma emitter for me. Okay, so what? Thin sheet of aluminium above the pellet of radioactive material to absorb the betas. The betas have a lower energy than the gammas. Sealed strontium have plastic cap above them. Yes, they do. So, okay, so it is emitting beta. We don't detect it because the sealed source, when we looked at it, we weren't looking at the cobalt-60 at all. We were looking at the aluminium sheet that is between the cobalt-60 pellet and the great outdoors, absorbing the beta so that only gamma is emitted. Now, I can't reference physics stack exchange, so I'll have to go into this and find something else to reference in relation to that. Drop and run, oh, that's fun. International Atomic Energy Agency. That's going to be perhaps something to reference or something like this. So you're going to find something that's worth referencing to that. But I'm not going to do that because, well, I'm not doing my A-levels, so I don't need to actually show I know how to reference. There's all the results. It's very close, not quite good enough for me for now. Hopefully you get better results when you do it. Bye-bye.